Hello viewers and welcome to the e-learning classroom. So today we want to look at 2021 physics paper 2, that is KCSE paper 2 2021. So let's go to section A. So we start with the first part, section A, with 25 marks. So question 1, figure 1 shows a ray of light incident on a plane mirror. Can see the incident ray, we have the mirror, we have the angle 30. Complete the diagram to show the path of the reflected ray. So we have the normal at 90 degrees or perpendicular to the mirror surface, and then the reflected ray such that the angle of incidence is equal to the angle of reflection. And also remember the two rays must obey the two laws of reflection. Let's go to question 2. Figure 2A, 2B, and 2C shows the process of charging an electroscope by induction. So we have the first setup, we have the second setup, and the third setup. It is observed that the lever rises in A, collapses in B, and then rises in C. Explain why the leaf collapses in B. It is observed that the leaf rises in A, collapses in B, and then rises in C. Explain why the leaf collapses in B. So we have a breathing load which is negatively charged, brought close to the cup. Then for B, we have earthing introduced. And then you realize also the negative charges on the plate and the leaf have disappeared, and the leaf has fallen. So in other words, the negative charges which are being repelled are neutralized by the earthing since they fall to the earth. The repulsion between the leaf and the plate therefore reduces when no charge is left between the plate and the leaf, hence the leaf collapses. So that is the explanation. In other words, initially the polyethylene rod induces negative charges on the plate and the leaf and attracts positive charges on the cup. But you realize when the earthing is introduced in part B, the negative charges which were being repelled are neutralized by the earth. That means the electrons flow to the earth. That's why they are neutralized. Let's go to question 3. State one use of capacitors. One use of capacitors. So are used in smoothing circuits, are used in tuning circuits, used in delay circuits, used to reduce sparking of contacts, e.g. in induction coils, and then are also used in camera flash systems. Figure 3 shows a graph of magnetic strength against time. We have magnetic strength against time for two nails P and Q when magnetized in a solenoid. P and Q are of the same size but are made up of different materials. So you have P and Q, magnetic strength against time, and then we have the two graphs. For A, identify the material that is magnetized faster. So the material magnetized faster is P. Use the domain theory to explain the answer in 4A above. So P dipoles in each domain are aligned faster in the same direction compared to Q and attains magnetic saturation state within a shorter time. So if you look at for the same time, let's say whichever time you pick, maybe after 1 second, for instance, you realize that Q has less magnetic strength than P. And that means P is being magnetized very, very fast. And also you realize the magnetic saturation point for P occurs at before that for Q. In other words, it attains the magnetic saturation faster. And that tells you again P is a soft magnetic material and Q is a hard magnetic material. So in other words, we are saying that is the reason why P is the one magnetized faster. Question 5. State the meaning of the term principal focus of a convex mirror. So principal focus is a point at which rays close and parallel to the principal axis appear to diverge from after reflection. Is the point at which rays close and parallel to the principal axis appear to diverge from after reflection. Question 6. Figure 4 shows a current carrying conductor placed between the two poles of two magnets. The direction of the current is into the paper. You can see current into the paper. There's a current carrying conductor. Then we have two magnets, north and south. Sketch the magnetic field produced between the conductor and the poles of the magnets. You can see there the field lines and also the force or the motion of the wire downwards. For that case, we are applying the Fleming's left-hand rule. Let's go to question 7. Figure 5 shows two coherent sources of sound, A and B, in phase. O is a point equidistant from A and B. So we have A and B. These are two speakers or two sources of sound. Then you have a line from M to N. An observer moves from M to N through Q. Remember, the two speakers A and B are in phase. Then the observer is moving from M to N through Q. Explain what is observed at point Q. Explain what is observed at point Q. So you realize that at point Q there is loud sound that is heard, and that is because that is a point of constructive interference. So Q is a point of constructive interference, so loud sound is heard, and the reason for that is that the two speakers A and B are in phase. So at Q, sound arrives at the same time at point Q, and they interfere constructively, meaning there will be loud sound that is heard. Question 8. State one factor that affects the speed of sound in water. One factor that affects the speed of sound in water, we have temperature and density of the water. These are the two factors affecting speed of sound in water. Question 9. Figure 6 shows a ray of light incident on a prism with a critical angle of 42. We have a ray of light incident on a prism. There's a glass prism. Then the critical angle is 42. Complete the diagram to show the path of the ray through the prism. So we can see the path, and then when it strikes the other surface, we have the emergent ray, whereby now the emergent ray deflects away from the normal because it is moving from denser to less dense medium. In other words, from prism to the hair. So it deflects away from normal because dense to less dense. And so for that part, let's go now to question 10. And it's also important to note that the reason why it is going away from the normal is that the angle of incidence on the second surface is less than critical angle. It is less than the critical. Because if you look at the angle, we have that here, we have 60, we have another 30. That means the angle of incidence for the second surface is 30 degrees. And that's why it is less than critical, and therefore it goes away from normal. Question 10. It is observed that when the heat current of the cathode, heating current of the cathode ray tube is increased, the intensity of the cathode ray increases. Explain this observation. When the heating current of the cathode ray tube is increased, the intensity of the cathode rays increases. Explain this observation. So the answer, increasing the heating current increases the thermionic emission rate, hence more electrons are dislodged, hence more cathode rays. In other words, increasing the heating current means the rate of thermionic emission increases, and that is why now we are saying more electrons are dislodged, meaning the intensity of the cathode rays increases. Let's go to question 11. A current of 2 ampere flows through a bulb for 2.5 minutes. A current of 2 ampere flows through a bulb for 2.5 minutes. Determine the quantity of charge that flows through the bulb. Charge. We have current and time, then you have to find charge. So we know Q equals IT. In other words, charge is current times time. So it will be 2 times 2.5 times 60. In other words, time in seconds. And that gives you 300 coulombs. Let's go straight to question 12. Figure 7 shows UV light passing through an aperture and incident on the cathode of a photocell. You can see the UV, you have the aperture, a narrow opening, you have a source of light or source of UV radiation. We have cathode, anode, and also millimeter. 12A, state what is observed on the millimeter when the size of the aperture is increased. When the size of the aperture is increased, so the millimeter deflects more. The millimeter deflects more. B, state the reason for the answer in 12A. The reason for answer in 12A. More UV light passes through the aperture, hence a higher number of photoelectrons are dislodged from the cathode, which are attracted to the anode, hence completing the circuit, and more current flows. More UV light passes through the aperture, hence a higher number of photoelectrons are dislodged. That is through photoelectric effect. More photoelectrons are dislodged from the cathode, which are attracted to the anode, hence completing the circuit, and more current flows. Question 13. State the property of radio waves that makes them suitable for use in communication. Property of radio waves that makes them suitable for use in communication. So they have longer wavelengths, hence are more easily diffracted allowed. The hills, they have longer wavelengths, hence are more easily diffracted allowed hills. In other words, you realize that radio waves can be able to the normal radius, you realize that they are more sensitive when it comes to the signal compared, for example, to the television. And that means radio waves, because they have the longest wavelength when it comes to the electromagnetic spectrum, you realize radio waves have the highest wavelength, and that means they are more easily diffracted allowed the hills and valleys and so on and so on. In other words, that's why now we are saying they are more preferred in communication. Let's go to section B. That one has 55 marks. So question 14A. State and explain how increase in temperature affects conductivity of a semiconductor. How increase in temperature affects conductivity of a semiconductor. Increase in temperature increases the rate of thermal conductivity of semiconductors. This is because increase in temperature increases kinetic energy of the electrons, which in turn enables the electrons to move from valence band to conduction band. And remember, for electrical conductivity to take place, electrons must be in the conduction band. So we are saying these electrons are able to move from valence band to conduction band when there is increase in temperature. That's why now the electrical conductivity of a semiconductor improves. Let's go to B, part B. Figure 8 shows a graph of potential difference V across a bulb against the current I through the bulb obtained from an experiment. Figure 8 shows a graph of potential difference V across a bulb against the current I through the bulb obtained from an experiment. We have V against I. Explain why part AO is straight. The resistance is constant. In other words, remember the slope. The slope of the graph change in voltage against change in current is resistance. And it's also important to know that anytime you're dealing with graphs, slope is very, very important. What does the slope represent? And also, what does the intercept represent? So we are saying if the slope is constant, and we are saying slope V over I, or change in V over change in I, is resistant, then it means resistance is constant. Roman 2, AB is curved. That means resistance is increasing with the increase in current. The higher the current, the higher the resistance, and that is due to the effect of heating. That is due to the effect of heating produced by higher current. Let's go to C. A circuit consists of 20 identical lamps connected in series to a 240 volt supply. A circuit consists of 20 identical lamps connected in series to a 240 volts main supply. Determine the potential difference across each lamp. So voltage is given by 240, which is the total, divided by the number of bulbs, because they are identical. So 240 divided by 20, which gives 12 volts for each lamp. Let's go to D. Figure 9 shows a circuit consisting of 2 identical lamps and 3 ammeters A1, A2, and A3 connected to a cell. We have 3 ammeters and we have 2 identical bulbs. Given that ammeter 1 reads 0.5, Roman 1, state the reading of ammeter 3. Remember, the 2 bulbs are identical, and ammeter 1 is in the main circuit. Remember, current flows from positive, splits are the 2 where we have ammeter 2 and ammeter 3, then combines and come back to negative. That means ammeter 1 is reading total current, which is now split into 2, where there is a junction and one passes through the 2 bulbs, equal current. In other words, reading of ammeter 3 will be total current divided by 2, which is 0.25 ampere. Explain the answer. So the reason for that is that the 2 bulbs are identical, and that means that current through each one of them is equal because the 2 are identical. Question 15. A. State the use of the high-piece lens in a compound microscope. Use of high-piece lens in a compound microscope. So the high-piece lens magnifies the image formed by objective lens. The high-piece lens magnifies the image formed by the objective lens. Question 15b. On the grid provided, draw a ray diagram to show how a convex lens forms a magnified real image. On the grid provided, draw a ray diagram to show how a convex lens forms a magnified real image. So we have the object between 12 and F, and then that's the one that forms a magnified image. Object must be between 12 and F, and then you realize you have a ray parallel to close and parallel to principal axis, which converges through the focal point. A ray through pole, which goes straight without any refraction, and that means now the image meets where the refracted rays are meeting. That's where the image is formed, which is magnified. The key thing is that you must know the 3 basic rays that we use to locate the image. There's a ray parallel converging through focal point, a ray through pole. We also have a ray through F, which goes parallel after refraction. So you can check even before drawing, you may be able to check for the 3, and then you're able to see where the image is formed. So let's now proceed to question 15c. Figure 10 shows a defect of vision in a human eye. Figure 10 shows a defect of vision in a human eye. So you can see the object, we have the eyeball, and then the image formed outside the retina. Roman 1, state the type of defect. So because this eye cannot see an object which is close to the eye, that means the problem here is long-sightedness. That is a defect, long-sightedness. In other words, this eye can see objects which are far, but it cannot see the objects which are near. So that is what we call long-sightedness or hypermetropia. State the type of lens that can be used to correct this defect. So you realize that because there is a converging far much beyond the retina where the image is supposed to be formed, you need to converge these rays before where they are converging. That is why we are using a converging lens or a convex lens. Then in Roman 3, on the same figure, draw rays to show how the lens in 15C Roman 2 corrects the defect. So we have the convex lens, and then we have when the incident rays reach the lens, they are slightly converged, and then eventually they meet at the retina. That is a correction, very, very important. You can see the diagram, and you also realize if you prolong the refracted rays, you realize like now the object has been brought far, and that is why now, because the eye is able to see objects which are further away. So D, figure 11 shows a graph of image distance V against the object distance U. Figure 11 shows a graph of image distance V against the object distance U obtained in an experiment to determine the focal length of a concave mirror. So we have V, image distance, U, object distance. We have a graph of V against U. Identify and mark a point X on the graph where V equals U. A point where V and U are equal. So you realize that one is occurring at 20 when V equals 20, because U is also at 20. So X will be on that part on the graph. That is the point where U and V are 20, because that's the point where the two are equal. Roman 2, use point X to determine, Roman 1, the radius of curvature R. Radius of curvature. So it means because U and V are equal, which is 20 centimeter, the radius of curvature is 20 centimeter. And in other words, what we are saying, object distance, the object itself is actually at C, the center of curvature. That means the radius of curvature from C to the pole of the lens. In other words, if you see that object and the image, it means the object is at center of curvature and the image is also on the center of curvature on the other side. Or F or 2F, sometimes we call it 2F. So we have 2F on this side and 2F on the other side. There's the object and the image. That means radius of curvature is in either object distance or image distance, which is 20 centimeters. Roman 2, focal length of the mirror. So focal length is half of radius of curvature, or radius of curvature divided by 2. So that gives you 10 centimeters. That is the focal length of that lens or the lens. 16A, state Faraday's law of magnetic induction. Faraday's law of magnetic induction. So it says that the magnitude of induced EMF is directly proportional to the rate of change of magnetic flux linkage. It states that the magnitude of induced EMF is directly proportional to the rate of change of magnetic flux linkage. That is Faraday's law. Remember, Faraday's law and Lenz's law go hand in hand, all in electromagnetic induction. So figure B, before you go to B, it's also important to note that when you're talking of Lenz's law and Faraday's law talks about the magnitude of EMF, the size was the quantity of induced EMF, but also Lenz's law indicates the direction. So Faraday's law, magnitude, we have Lenz's law, the direction. So B, Figure 12 shows a bar magnet being moved towards a solenoid. The solenoid is being connected to a galvanometer. You have solenoid, galvanometer, motion of magnet towards D. Indicate on the diagram the direction of the induced current in the solenoid. Direction of induced current. So first, you have to note that because the magnet is moving towards the coil based on Lenz's law, then end D must form a north pole to repel the magnet. End B must form a north, and we know north pole based on Crock rule. Based on Crock rule, north pole has anti-clockwise current. That means it will be up on this on the front and down behind. So it is anti-clockwise current. That's why all the for all the coils on the front side it is rising, behind is falling. Identify the pole induced at D. Of course, that is north pole based on Lenz's law. Explain the answer in 16b Roman 2. So from Lenz's law, the induced current creates a magnetic effect that opposes the change causing it. Hence, a north pole is created on end B and D in order to repel the magnetic motion. So that is based on Lenz's law, whereby we are saying now the induced pole must repel the motion of the magnet. That is but you have to give an explanation that can give you 2 marks. That's why we are highlighting the whole explanation. Roman 4. Apart from the number of turns in the solenoid, state 2 factors affecting the magnitude of induced current. Magnitude of induced current. We have a number of turns of coil which you have already given, and you are told apart from that. So the other factors include speed of motion of the magnet, the speed of motion of the magnet, and then we have the strength of the magnet used. The strength of the magnet used. Explain how laminating the core of a transformer, increases its efficiency. Laminating the core. So laminating the core reduces the eddy currents, hence lowering the heating effect, and efficiency increases. We have said lamination reduces eddy currents. Remember, that is the essence of laminating, to reduce eddy currents. And eddy currents, once they are reduced, even the heating effect will also be reduced. And therefore, efficiency will improve. 17a. Explain how a fuse protects electrical devices from damage. How a fuse protects electrical devices from damage. The fuse normally melts when the current exceeds its rating, hence disconnecting the device from the circuit with excess current or stopping the flow of current in the circuit. In other words, when current exceeds a certain rating of the rating of the fuse, then it means that the fuse will blow or the fuse will melt. Therefore, it will disconnect the current or it will stop the flow of current. B. State and explain why the voltage in the mains electricity is stepped up before long distance transmission. Essence of stepping up voltage before long distance transmission. Stepping up voltage helps in minimizing power loss during transmission. That's a key point. Stepping up voltage helps in minimizing power loss during transmission, since stepping up the voltage lowers the current, which in turn reduces the heating effect on the cables, hence minimizing the resistance of the cables and power loss. In other words, when you step up voltage, secondary current will lower or will be reduced, because power must remain constant. The power input must be equal to the power output, and therefore when current is reduced, it means heating effect is reduced, because remember, heating effect, when the current is high, even the heating effect will also be high, because power it is given by I squared RT, that's current squared times resistance times time. Let's go to C. Figure 13 shows how power can be transmitted from the generating station through transformers P, Q, and R to the consumer. We have the generation station, power station, transformers P, Q, and R, and we have the consumers. Identify the type of transformer labeled P. So let's look at the power voltage input for P. 11 kilovolts, that's the primary voltage. Secondary voltage 133 kilovolts. Definitely that you can see that the voltage has stepped up from 11 to 133 kilovolts. That means P is that step up transformer. Roman 2, explain how the number of turns in the primary and secondary coils of transformer P affects its output voltage. Number of turns in P. So it has greater number of secondary coils than primary coils, hence the output voltage is higher than the input voltage. In other words, it has higher number of primary coils than secondary coils. No, sorry. It has a higher number of secondary. Secondary coils are higher than primary coils. Secondary coils are higher than primary coils. In other words, that means because secondary coils are more, then it simply implies that voltage will be stepped up. In other words, secondary voltage will be higher than primary voltage. So we go to question Roman 3. State the reason why one of the wires from R to the school should be earthed. We have R, that is a step down, which is stepping down to 240 volts, while one of the wires is earthed. Remember, if you look at the wires, we have 3 wires from station to P, 3 from P to Q, 3 from Q to R, but we have 2 from R to school. That means from R to school, we have live wire and neutral wire. So the essence of earthing, actually earthing is done on neutral wire, and the essence is to keep it neutral. In other words, to keep it at 0 potential or 0 voltage. Let's go to question D. A power station generates 11 kilovolts at a current of 1 ampere. A power station generates 11 kilovolts at a current of 1 ampere. The voltage is stepped up to 160 kilovolts before being transmitted through electric cables. Assuming the transformer is 100% efficient, determine the secondary current. So 100% efficient means power input is equals to power output. In other words, current of primary times voltage of primary is equals current of secondary times voltage of secondary, and that gives you current of secondary is 0.069 ampere. The key thing is to note there is that 11 kilovolts means 11,000 volts, because kilo means 1,000. Let's go now to question 18A. Question 18A, so the last question. Figure 14 shows a cathode ray tube. A metal plate is placed between the anode and the screen. So we have the filament, we have the cathode, the anode. We have a metal plate, so like an obstacle, and then we have the screen. Roman 1, state with a reason what would be observed on the screen when the cathode rays are produced. A shadow of the metal plate is casting on the screen. That is what is observed. A shadow of the metal plate is casting on the screen. Roman 2, state the effect on the cathode rays produced. So we go now to Roman 3. State the effect on the cathode rays produced when the anode potential is increased. The effect on the cathode rays produced when the anode potential is increased. So when you increase the anode, remember the anode is the one that is accelerating the electrons towards the screen, because anode is positive and the electrons are negative. So in other words, the speed of the cathode rays towards the screen is increased, or the speed of the beam of electrons towards the screen is increased. B, explain how X-rays produce photographs of fractures in bones. How X-rays produce photographs of fractures in bones. X-rays are absorbed by the bones, hence there is retro exposure to the film, while X-rays pass through the flesh and bone fractures with greater exposure, hence the images of fractures are formed on the film. In other words, we are saying X-rays are able to move and to propagate through the flesh and also the bone fractures where there are cracks. That means where there is a bone itself, the X-rays will be a bit blocked, and that means a shadow or the image is formed on the film. Let's go to see. Figure 15 shows a monochromatic light incident on the cathode of a photocell connected to point P, Q, R, and S through a jockey. So we have monochromatic light, anode, cathode, we have a jockey, and then we are told state what will be observed when the jockey is connected to P. The ammeter deflects, indicating flow of currents. That's the observation. Then Roman 2, connected to point P to Q to R and then to S. In other words, when you move the jockey from P to Q, then to R, and then finally to S. That means these are cells, by the way, between Q and P, cell, R and Q, cell, S and R, cell. And you're also observing the direction of current. So the ammeter deflection or reading increases gradually. The ammeter deflection increases gradually. Explain the answer in C Roman 2. Explain the answer in C Roman 2. So as the applied voltage increases, more electrons are dislodged from the cathode, which in turn are attracted to the anode, hence more current flows through the circuit. In other words, you are saying as you increase the voltage, it means now more electrons will be dislodged from the cathode, and then they will be attracted to the anode, and then that means now the current flowing will now increase. State how radioactivity may be used to detect oil leakage in an underground pipeline. How radioactivity may be used to detect an oil leakage in an underground pipeline. So the oil is mixed with a radioactive substance at the source, and where there is a leakage, the radioactive mixture seeps out, and a radioactive detector passed nearby is able to detect where there are radiations, hence the leakage. In other words, you mix the oil with a radioactive substance, and then as the oil moves through the pipe, in case there is a place where there is a leakage, then it means even the radioactive substance will seep out through that leakage point. And if you pass a detector, e.g. GM tube or a Geiger tube nearby, then you're able to detect the radioactive substance that is seeping out through the crack. In other words, you're able to detect where there is a crack. So that is the end of 2021 physics paper 2, and that is what was expected of you in that paper. You realize it's a very simple paper, but it has several scientific concepts, and that means it's enough for you to be able to understand how you prepare for the next examination. So that marks the end of today's session. Let's see you in the next video.